So in the last lecture, we introduced the finite element method as a way to solve basically optimization problems, right? To solve the kind of problems that can be formulated into minimizing over the space of functions a particular scalar objective function, right? And we have also shown an example of how to turn partial differential equations into this kind of optimization problems. All right, and let's actually review that. How do we turn Poisson's equation into an optimization problem that can be solved using finite elements? And then we proceed in discussing exactly how to formulate the linear system that can be solved on the computer. Okay, so today we are going to be looking at particularly the Poisson's equation d square u dx square plus f equal to 0. Here, f of x is a given function. It's a function that is already known. We also have boundary condition u at 0 on the left side of the domain is equal to u at 1 on the right side of the domain equal to 0. So that completely defines the solution to the partial differential equation. All right. And let's see how do we turn this into a optimization problem. And particularly, we are going to turn it into what's called the weak form of the differential equation. And all finite elements is discretizing the weak form. And this is, let me take this opportunity to review a little bit of the three methods we learned: finite difference, finite volume, and finite elements. In finite difference, we directly discretize the differential equation, the differential form of the equation. In finite volume, we integrate the differential equation over an arbitrary domain, right? Over an arbitrary interval in 1D and an arbitrary domain in 2 and 3 dimensions, and solve the integral form of the equation. In finite elements, we solve the weak form of the equation. The weak form of the equation can either be derived from an optimization problem, as we have seen in the last lecture, or it can be derived from the, we call the strong form or the differential form of the differential equation. By doing something very similar to what we do in finite volume, but a little bit more complicated. It is also by integrating the equation. But before we integrate the equation, we actually multiply the equation with what's called a test function before we integrate it. Okay, let me try to do it here. So because we know this equation is equal to 0, so if we multiply any function v of x to the equation, okay, so that turns the equation into v times second derivative of u plus f, right? That's still equal to 0, right? Because what's in the parentheses has to equal to 0 for any x. So you multiply this with any function, it's still equal to 0. Then we integrate. We integrate over the entire domain from 0 to 1 dx. Now here's a primary difference between finite element, the weak form of finite element, versus the integral form in finite volume. You can say that the integral in finite volume is actually a special case of this type of integral, in that our v is actually equal to either 0 or 1. It is 1 in the domain we're integrating, right, from L to R, if we're integrating over the domain L to R, and 0 outside the domain. So if you pick v to be this kind of what we call indicator functions, then we go back to what we are doing in finite volume. In finite element, we are actually generalizing that type of integral form into what we are calling the weak form now by multiplying the whole equation with an arbitrary function v. Okay, and actually not exactly arbitrary function. We are multiplying this with actually a differentiable smooth function. Unlike in finite volume, we are multiplying with the indicator function, either 0 or 1, it's discontinuous. In finite element, we are multiplying with actually, let me say, differentiable function v. Okay, so v being differentiable enables me to actually manipulate this integral into something weaker, into something that allows me to weaken the differentiability requirement of u. And the method we are going to be using to do that is integration by parts. Okay, integration by parts. So integration by parts basically says that if I have an integral from 0 to 1, I have a v of x times a second derivative of another function u. It can be written, it is equal to the negative of the same integral, and I put the v, which was originally not differentiated, into a derivative, and the u can be taken out of one level of derivative. Okay, so both are integrated over dx, and there is a boundary term. The boundary term is v times the du times du dx, which is basically the second term in the original equation taken out of one level of derivative. Okay, and this is not integrated, but rather taken at the boundary, the difference between value at 1 and from value at 0. So this is what we call integration by parts. Are you familiar with how the integration by parts works and how it is derived? Anybody?
I've seen it before. Yeah.
Okay, good. So it is basically derived. If you want to derive it for yourself, it is basically derived from the ddx, applying the fundamental theorem of calculus to the derivative of f times g for two functions f and g. Right? Basically, this from 0 to 1 is equal to fg 0 to 1, right? And here my f is actually v, my g is du dx. So if you apply this, you're going to figure out, you get integration by